you so much for the function for giving this opportunity. And definitely, it's good that Mobility Outlook has taken this initiative because often what happens is we don't talk about the problems and a roadmap. So it is heartening that in all the conversations that we have had, people have been candid about the problems and how to go about, because the first step in the journey towards finding solutions, sustainable or otherwise, is to actually acknowledge there's a problem. So my compliments for that. So essentially, I would be just briefly covering under this following heads. So since it's a technology session, I have put in a little bit of a technology part of it as to what we are doing. And in the next few minutes, I will try to share about our journey and as to why we chose what we are doing, how we see the technology panning out, especially in the motor development scenario, and maybe a few pointers as to where we see the EV space evolving in the coming few years. We started our journey with the intent of mainstreaming axial flux motors, and we targeted the EV space because that was the first go-to market where there was a value proposition. And in the larger scheme of things, we want to have axial flex machines coming out for other applications as well. So, yeah, I mean, the question that's often thrown to us is what prompted you from a naval whites to this extremely disconnected area of machine design. So we keep telling them that we were trained in the Navy to become electrical engineers, and as part of that, virtually you handled every facet of electricity when on board ships and submarines. So you have dealt with motors or generators all our lives. So from a user, now it was about, okay, getting onto the design board to start doing it. So it was not very unconnected insofar as what we are doing now. But yes, the only difference being from a user, now we had donned the hat of a creator. So that's how it started. And there was a time when in 2018, we were about to move on from the naval career, and EVs were coming into the fancy. And the idea was that since we had used, there were a lot of work that had been done in the Navy to reduce weight and volume, because that's pivotal when it comes to warships and submarines. So we were aware about the axial flux technology, and our idea was essentially that IC engine architecture is there existing, but EVs allows us to think out of the box and look at solutions which can be customized, because IC engine developed with the boundaries set in by the internal combustion engine per se, which was limited in its capacity to generate high torque at low RPM, whereas motors didn't have that particular limitation insofar as the design part is concerned. Yes, there were certain other challenges, and our aim was to cross that bridge. So we are fortunate that we could raise our seed investment from Gale, because hardware R&D is expensive, and without money you can't do much. And subsequently, we got incubated in IIT Delhi, and we continue to be here, which allows us access to the bright minds, which allows us to get hold of the academic rigor, which we need once in a while. So why machine design? Because we are very good assembly line manufacturers. Designs have been coming into our country, and we are probably second to none insofar as manufacturing something is concerned. And we've been on the receiving side of this whilst being in the forces as well, where niche technology comes from somewhere else, and it comes with a lot of ifs and buts and a lot of controls. So there's not much of flexibility that one has. And so is the case elsewhere as well. 2018 was a time when everything was coming in from outside, and it was more of an integration that was happening in the country. So our idea was that we believe that a motor is the biggest consumer in an EV, and it cannot be the standard motor that we've been seeing in our industries and houses, which operates in a completely different regime. And in the EV, when it comes out, it has to operate extremely at the opposite end of what a conventional motor in the industry operates at. So the idea was that design would come to the fore as we go along. And unlike the IC engine, EVs allow us to make the motors in as many variations as one wants. I mean, if I'm going to operate a vehicle, say in a plain area where there are not many, heights and the terrain is flat, I can have a different design for a motor. Whereas if I'm going to majorly operate in a hilly area, I can customize the motor in a manner so that it enables that particular function. So that can only happen when you have captive capability of designing motors in that particular manner. So our idea was that we should design the motors to operate in our conditions, which are very different from the places where most of the development so far has been happening. So you had to push the thermal environment right up there to ensure that the motors operate without failures. And the idea was, again, I mean, we are a huge country, and if I can have an open canvas and I can develop a motor for what the OEM wants, it enables them to power their dream wheel. So that was the whole idea with which we started the journey. So just to give you a context, I mean, I have just put one particular design which we have made and which is getting commercialized. So if you see, the spec looks very innocuous, 48 volts, 8 kilowatt, 40 Newton meter. But the whole story starts unraveling beyond that. I mean, how much time you need the 40 Newton meter for? I mean, at what speed do you want the rated RPM? And uh, what is your S2 cycle? What is your uh, duty cycle? So these are the questions which often get lost because people pick up, okay, I need an 8 kilowatt motor. But beyond that, because everybody is coming up to speed, trying to get data, there's not much empirical data available because all these factors ultimately impact the motor design. I mean, just to give you, I just put this slide in the front so that I could contextualize as to what I mean by this. I mean, if somebody says, say, I need a rated RPM of 2,500. So, and he says, okay, I need a peak torque for a minute or 1.5 minutes. So my design, my iron, my copper, my magnet, everything gets decided with that. And obviously, you want a wider efficiency band, the material has to go in because it is laws of physics. At the same time, somebody can come with me and tell me I need a 8 kilowatt motor, 48 volt, 40 Newton meter, but their requirement may be a peak torque only for a minute or a higher rated RPM. So a lot of dynamics about the current limits and everything changes. So if one doesn't understand this aspect when you take up a design, you will have a motor which is 8 kilowatt, but it will never give you the performance what we envisage. So this is what we feel that has to be given on the table for the vehicle OEMs so that they can actually have the flexibility to have a motor which is more suited for their particular application and their particular requirement. I mean, it's simple. I mean, many of us grew up wearing tailored clothes. So more often than not, they would fit us absolutely fine. We started getting the ready-made brands. There were so many brands. Now, all of us, depending on our form fit, find certain clothes of a brand which fit us and certain don't. So this is exactly something like that. I mean, you can pick up something which is ready-made, but till the time you don't go through the iteration, you will never know if it's fitting your requirement. And at the same time, if you have the time and availability and the resources to put in, you can always go back to a customized solution which can actually give you what you're looking for. So now, with that in context, I just probably take few minutes to tell as to how we go about our journey when I do the motor sizing so that I design it accordingly to the requirement of the OEM is met. So the first instance, it is essentially we try and go threadbare with the vehicle OEM as to what is it that they want. And many a times, some of the answers even they don't have, some of the answers by virtue of our work so far, whatever we have gained, we try to share with them. And then we build up a broad matrix. Okay, this is what the vehicle is intended to. And these are the particular dimension and the targets and the constraints that are defined. So this is a mutually done activity. And we share our particular perspectives as to if something has to be done, what is the flip side of it, what is the advantage, so that both of us are on the same page. And once this particular exercise is done, thereafter, we take it forward for the design part of it. And we define the broad parameters of the motor, which then necessarily impact the other part of the selection of the controller or the BMS or the battery pack and the sizing. So once this is done, that is where our actual journey to design the motor starts off. And thereafter, there are various factors. I will not go through them one by one, but these are some of the factors that come into picture when we are working on our particular analytical analysis of it. And then we put it through a particular data set that we have created over the period of work that we've been doing with multiple players. And we try to size it in a particular form factor. And here we keep it in mind that whatever is available in the ecosystem, which can be taken up straight away. I mean, say a casing which is available readily as an extrusion, or a particular bearing, so that we minimize on the cost element, because ultimately design can be done with anything, but ultimately it has to stand at the altar of the price. And thereafter, our work on the simulation starts. We use Dassault Opera for our FEA because we chose that specifically at that point of time, because Axial Flux per se needs 3D analysis and 3D simulation. And that was the most potent tool at that point of time when we're in industry. And the same tool we use as well for our radial flux design. And thereafter, once the model is ready, then we do the static analysis and the dynamic analysis so that my broad contours of the design are frozen, which subsequently is taken forward for the thermal and the structural design aspects. Which after this, once all this has been done on the simulation, we cull out all the performance curves and efficiency maps. When we did our initial set of prototyping, our delta was around 4 to 5%. But now with the repetitive exercise that has happened with multiple prototyping, our simulation as vis-a-vis what we achieve is virtually there. I mean, because in simulation, in prototyping, we tend to have a little bit of a higher losses because you resort to laser and some other machining processes which are not exactly electromagnetically the most suited. But when finally you go on to production processes, they become much more refined and your losses come down. So now we are at a stage where essentially what we simulate and what we achieve is as good as there. So of course, that is because we have built in those errors in our designing methodology. So this is something which I just want to take probably a minute to show. I mean, when we started like radial flux designs, you have a lot of templates which are available in the tool, so which make your journey to a closer form factor much faster. But in Axial Flux, there was nothing existing. So when we started moving every step, we started customizing and scripting our own requirements, so that what you see on the screen is one of the modeling that we have done, which is for a surface-mounted axial flux motor with single-stator dual rotor. We called it Quanteon Jarvis because we are all Marvel fans, and the Iron Man calling out to Jarvis or something we want to. In fact, we want to integrate voice-driven commands as well. So maybe sometime down the road, the next time you would be having someone telling that this is my rotor diameter and this is the thickness. And so essentially, we did this particular model because it enables us to do my model very, very fast. I mean, after the analytical calculation, it is just about inputting the data and my model is ready. This, incidentally, initially we would take nearly 5 to 6 months to get this model right, because like every tool, there are certain pluses in some and there are certain minuses in this. So in Opera, we used to have a lot of challenges in making the winding, and it would take us a lot of time. So every time we went through that pain, we ensured that we started tabulating it, and then we made this particular tool, which enables a particular part of my journey to become much, much streamlined. So to put it together, I mean, this is the journey from when somebody shares to how we go about to finalize a design, which then goes on to the prototyping cycle. So since I was put in the technical session, I took the liberty of just sharing this particular aspect of it. So now coming out to the discussion of the day, that what is the future? I mean, I probably would put a caveat that it's no longer the future. We are actually in it. I mean, 3 years back, maybe electric cars and electrical vehicles were the future, but today you are actually living it, and probably they will be all around us in no time. So by electric in this, I actually mean the literal meaning that it is actually very, very exciting times for the automotive space. And we believe that axial flux motors would find favor going forward for very many obvious reasons, that it enables us to reduce the use of material, be it copper or iron. And as somebody allayed in the previous session, that will you move away with inline motors? So the very fact that we started this journey was we could take the power into the wheels. So why axial flux is so power dense is just a matter of geometry. On the left is what we conventionally know as the radial flux motor, which are two coaxial cylinders, and the surface area of the rotor, which is the green part inside, is the one that gives you the flux, and that's how you get the power and torque. On the right is the axial flux, where you move on to the sides. So in the same diameter, if you don't increase your length in radial flux, the axial flux gives you much higher surface area, and surface area directly correlates to the amount of flux you can generate. And as a result, you have motors which are like a disc, which are very, very short in length, and they will just have a little bit of a diameter based on a design. So theoretically, you can have 7 times power dense and torque dense motors. But yes, machining aspects, if you put aside, you're able to cut it down sizable. I mean, up to half reduction. I mean, you can reduce your bill of material by nearly 50%. So some of the other aspects which come into the machining part, you can use grain-oriented steel, which is otherwise called as a transformer steel. And all of us know that the transformers are the most efficient machines because your core losses are much lesser. Conventional motors use non-grain-oriented steel. Likewise, you can use rectangular cross-section conductors, which gives you much higher fill factor. You have concentrated windings, so your end-turn losses, which are a prominent loss in the radial flux machines, are non-existent. And the fact that in certain design, which we are working on, known as the yokeless design, you have a single stator and 2 rotors. So you are absolutely maximizing the flux utilization. In fact, if you see in the last 2 years, virtually every second day, you would find somebody putting a different type of motor, which is more power dense and more torque dense. And people are working on multiple topology. They call it radial and axial. So virtually what they're doing is wherever there is flux, which otherwise earlier was getting lost, you are trying to maximize and eke out the last bit of juice out of it so that you can have a more power dense and torque dense motor. So this is essentially what an axial flux motor looks like. I mean, you can just see the difference. Probably I will just share in the next particular slide. 2 of our motors designed, one in radial flux topology and one in axial flux topology, and the kind of weight saving you can do. So our idea is this technology has remained niche because there were a lot of challenges insofar as the production processes are concerned. And that is what we've been working on the last 3 years, in which we have developed every particular facet of it to ensure that this can translate into a cost-effective, seamless volume production product. So that is what our aim has been, and we probably are nearly there. So just to give you a comparison, I mean, on the left is the same motor which I shared earlier for a 3-wheeler L5 category. And the comparative motor, yes, it's a PMSM, so it has got magnets. But despite that, if you see the cost, the reduction in the iron and copper is substantial. And going forward, I'm sure we will have topologies of induction also coming into axial flux, which will again be much more using much less iron and copper compared to the radial flux machine. So that is something that is there now. It is for the taking. And in a way, it was good that Mercedes acquiring Yasha became good news. And a lot of people were working on. Then Wylot was invested in by Renault. And globally now people are looking up to this particular technology. And as more and more people start getting invested, it's natural that it will come to the fore and it will start getting mainstream. So now coming to the work that we have done to ensure that this can see the light of day and fine. So what you see on the screen is a 19-inch diameter, 5.5-inch wide motor, which can generate up to 1,200 Newton meters of peak torque. And all our designs we've been mindful that we have been doing it with passive cooling, and that too for our Indian conditions. So if I introduce cooling, I can push this torque even higher up to about 2,000, 2,200. So our idea was that in a 19-inch frame, this could go into a 30-seater bus, rear wheels, and it is good enough to power it. Likewise, we chose the second diameter was a much smaller one, 11-inch. So our idea was all the 2-wheeler requirement can be met in a small frame of 11-inch diameter, 4-inch thick motor, which could go into the rear tire of a 2-wheeler, and it could give the power. Thereafter, we also moved to a high-speed motor because it's a translation. Whilst we have the capability to make hub motors which are power dense, but the chassis development needs to happen. So it is work in progress. We are working with certain agencies who are working on very customized solutions.
I'm sorry to interrupt you, Commander, but the time frame.
1 minute. 1 minute. I'm just going to finish. That's it. So this is the motor that's been for a high-speed RPM. Now this is also tested and it will go into the vehicle. Now somebody allied to an e-axle. An e-axle with an axial flux motor is also under development, which will not take away the differential, but will get directly coupled to the differential. So this is broadly what we have done insofar as the axial flux topology is concerned. So what we see is any type of motor which is custom designed for an application will find space, whether it is magnetless or magnet, it doesn't matter. But yes, for certain applications where you can do with magnetless, it would remain, as Mrs. Tikku referred, that you need supply lines which are local. So that is where the magnetless motors will find favor. Axial flux machines will start proliferating, and e-axle designs in the CV space, and what we call as hub motor, which is direct drive, independent wheels getting powered, is something which is already there, and it's going to just find more and more utilization. What you see on the screen is the left is a Japanese car, which is with two front wheels as hub motors. Hitachi is already working on their concept in which all the four wheels are. On the right is an Israeli company. There are few more in Lordstown and Rivian. So all of these are in wheel, which will again is an architectural change as to what we see IC engine. So yes, the charity should begin at home. So I end my call. Apologies for the slight overshoot. Thank you so much.
Thank you, Commander. Wonderful session. Now I request Mr. Sahil Bangia, Spatial Projects Manager, Vehicle Certification Agency, to take over and start his presentation.
Today I'll try to cover this big question, whether EVs are safe and pollution-free. So what I'll be covering is the alternative fuel options, which I guess many speakers have already covered. Then the two basic questions: are EVs pollution-free and are EVs safe? Then we'll go through the European regulatory mechanism, and then a short description about VCA and VCA India. So we all know why alternative fuels. There's a climate change, rapidly growing import bills for oil, increase in city air pollution, and fossil fuel depletion are the main reasons why we want to go for alternative fuels. The options, alternative power options, electric mobility, we are already in. Then we have green hydrogen. Government has some huge plans for green hydrogen. We have LNG, biofuels, ethanol blend fuels, of course, solar and wind. So now coming to the first question, are EVs pollution free? So before answering this question, let's go to the India's mobility fuel requirement. India has the largest line network, rail network in the world, second largest road network in the world. About 70% of India's energy requirement are fulfilled through imported fossil fuels, which in short turns out to be a huge import bill. India consumes about 30% of the world's fossil fuel needs, and INR 8 lakh crore are spent on oil imports, which account to about 3% of the national GDP. So India's future policies and vision, like what is kept in mind while designing the policies, is obviously the energy security, the infrastructure development, low-cost mobility for all, reduction in air pollution, employment generation, obviously, and how to achieve all these objectives is through the PLI schemes, which we have seen recently for the many sectors, exemptions and loan facilities, Make in India campaign, and reduction on oil import bills. This is the general energy mix of India. The data sources from International Energy Agency. So over 80% of India's energy needs are met by three main fuels, which are coal, oil, and solid biomass. So coal, as we all know, has underpinned the expansion of electricity generation industry and remains the largest single fuel in the energy mix. Oil consumption and imports have grown rapidly on account of rising vehicle ownership and road transport use, and biomass is primarily used as a cooking fuel. So renewables, as we see, are still 3% in the entire energy mix. Coming on to the future powertrain options in transportation. Actually, each segment of transportation might require a different viable option of alternative fuel in future. So if we talk about electric vehicles, and that is good for the short ranges as we are facing challenges regarding the range and the charging infrastructure. So electric mobility is good for L category, two-wheelers, four-wheelers, and short range commute. Whereas the hydrogen and LNG remains the good options for future commercial vehicles for the long range transportation. And obviously, one of the drawback is LNG that it evaporates very fast, so it cannot be used for the short range commute. Now this pie chart explains the total energy consumption of India. So if we see this import dependency, we have oil 85% import, coal 24% import, gas 53% import. And out of the total energy mix, only 18% is utilized to create the electricity. So how this 18% electricity is generated, 74% through coal, 9% through hydro, 5% natural gas, and 12% other renewable resources. Now, this is a very good study that has been done by a top consulting firm. So it talks about the well-to-wheel efficiency. So if you talk about IC engine vehicle and we talk about the well-to-tank, so that is 83% efficient. If you say here, this is for the IC engine vehicle. And for an electric vehicle, the well-to-tank efficiency is 30%, only 30% efficient. But the turnaround is the tank-to-wheel. So in tank-to-wheel, the electric vehicle becomes 80% efficient and the IC engine vehicle becomes 20% efficient. So overall, if you talk about the overall well-to-wheel efficiency, so electric vehicle is 24% efficient and IC engine vehicle is 16% efficient. Saying that, so we can conclude by this study that electric vehicles are much cleaner even when charged on the electric power grid. So if you see this is the gasoline vehicle and the annual well-to-wheel car emissions emitted by the gasoline vehicle. CO2 obviously is very high. We have a huge amount of NOx and PM 2.5. Whereas for the EV charged on grid, mix of sources, coal, nuclear, wind, gas, we have reduction in CO2, we have reduction in NOx and also PM 2.5. And obviously in future, if EV charged with renewables, then we go to a zero emission value. So answer to our question, are EVs pollution free? Not entirely, but much cleaner than IC engines and have a scope to become 100% pollution free. Coming on to the next question, are EVs safe? So recently we all have seen these cases of fire in the two-wheeler battery motor. At high temperatures, they are catching fire. Which brings to the next topic about the principle of type approval, like the basic principles. There's a social demand, social necessity from safety and environment, minimum safety requirement, performance requirement from the vehicle, obviously technological advancement, harmonization with the global market, and conformity of production. So we all know EVs are gaining popularity in the marketplace. Hence, it is imperative for the manufacturers to ensure safety of the public. Widespread adoption will also require ease for the use of consumers, and a robust testing and certification type approval can help to meet all of these requirements. Categories of electric vehicles as per regulatory framework we have. So there can be a different testing and certification requirement for a different category of wheelers. We have off-road vehicles which runs within the campus. We have two-wheelers less than 250 watt. We have e-rickshaw, e-cart, which has speeds less than 25 kmph. Then there are four-wheeler passenger vehicle, M1, N1 category. We have electric two-wheelers, e-auto, and heavy vehicles. So the testing and certification can differ for all of these vehicles. Some obviously have been exempted. Now, if we talk about electric vehicle testing, there are four major parameters. Verification, which is common for the electric vehicle and the IC engine vehicle, wherein the functional construction, telltales, lighting and signal, and all these things are verified. Then safety, electric shock, water effects, RESS safety, crash and after test, EMC becomes very important for the EVs. Then on performance side, we have range, energy consumption, power, gradability, max speed and brake. And finally, the approval wherein we process the documentation and verification of approved components. Now, if I talk about specific to EV regulations and compare the Indian standards with the European standards, so there is ECR 100, which talks about the safety of the battery, requirements for construction and functional safety, and which is in parallel to AIA 038. Then there is ECR 101, which is the measurement of electrical energy consumption, which is in parallel to AIA 039 in CMVR. Then ECR 101 again talks about the method of measuring the range. And we have for the powertrain motor, net power and maximum 30-minute power, ECR 85, and in CMVR AIA 041. So talking about the vehicle battery approval for M and N category. So in Europe, there are two different standards, R100 for the M category and R136 for the L category, which covers the two-wheelers. So most of the tests in R100 and R136 are almost similar. They all are for the safety of the battery and electrical vehicle as a whole. Talking about the list of tests, so there are 10 basic tests. Vibration test, thermal shock and cycling, mechanical test, shock, mechanical integrity, fire resistance, external short circuit, and there are 4 functional tests: overcharge, over discharge, over temperature, and over current. Now I'll be explaining these tests in the next few slides, and the aim is to show that if type approval sequence and testing is properly followed, then how can we conclude whether EVs are safe or not? So before that, just a background to the ECR 100 regulations. So just to summarize, the UNEC, United Nations Economic Commission for Europe, is one of the 5 regional commissions for United Nations Economic and Social Council. It consists of 56 member states, which includes European countries, plus the United States, Canada, Israel, Turkey. The aim of the commission is to converge the approval procedures between the member states. And for that, 3 UN agreements, which were adopted in the year 1958, 1997, and 1998, they provide the legal framework for WB29 to establish regulatory instruments for motor vehicles and their equipment. Within UNEC, there are many formal and informal working groups that take care of the passive safety, emissions, RD, and all. Now coming back to the R100, starting with the construction and functional safety, there is traction, battery mounting, ventilation details. These are all required from the manufacturer to submit to the test authority. Then the test against electrical shock, connection of vehicles to mains for the charging. Then there are audible or visual indicators that are tested. Obviously protection against water effects, washing, flooding, all these are tested. There is a specific requirement of high voltage marking that is mandatory on the battery systems. Then there are motor tests. There is electrical energy consumption, which gives the reading in watt-hour per kilometer, which is basically determination of electrical energy required from the mains for charging per kilometer of travel. And this test is basically done on chassis dynamometer. Measurement of range, again a test on in the lab. So India is following MIDC, Europe is following WLTC for that, and the kilometer that is covered in one complete charge is determined through this test. Then obviously for the motor we have measurement of net power and maximum 30-minute power. So this is similar to the engine power test, which is a representation of the curve of motor speed and power at full load for electric drivetrain. Now coming into the details of the battery safety test. So first on the vibration test. So what is the aim? Purpose is to verify the safety performance of a rechargeable energy storage system under a vibration environment, which the vehicle will likely experience during the normal operation of the vehicle. So as you can see, the tested vehicle, the device is firmly secured to the platform of the vibration machine. in such a manner as to ensure that vibrations are directly transmitted to the tested device. So this is a simulation based testing. So the tested device shall be subjected to a vibration having a waveform with a logarithmic speed between 7 hertz and 50 hertz and back to 7 hertz in 15 minutes. And this complete cycle is repeated 12 times for a total of 3 hours. And after this test is completed, the acceptance criteria is basically visual. There should be not any evidence of electrolyte leakage, rupture, fire, or explosion. Then coming on to the next test, thermal shock and cycling test. Again, the purpose of this test is to verify the sudden how the battery system will react to sudden changes in temperature. So as you can see, this covers the big temperature range, 60 plus minus 2 degrees Celsius at the higher end to minus 40 plus minus 2 degrees Celsius to the lower end. So in this test, after storage of 24 hours, a standard cycle is conducted, and the test shall end with an observation period of 1 hour at ambient temperature conditions of the test environment. Again, the acceptance criteria remain same during the test or after the observation period. There should be no evidence of electrolyte leakage, rupture, fire, or explosion. Moving on, another very important test is the mechanical shock test. So the purpose of this test is to verify safety performance of the battery system under the loads which may occur during a vehicle crash. So this test can be done entirely on the vehicle during the crash or individually on the battery system. Acceptance criteria remain same. There should be no electrolyte leakage, rupture, fire, or explosion. Our next very important test is mechanical integrity. The purpose of this test is to verify the safety performance of the battery system under contact loads, which may occur during vehicle crash situation. So this is again how performed the tested device shall be crushed between a resistance and a crush plate with a force of at least 100 kilonewtons. And again, the test shall end with an observation period of 1 hour at ambient temperature conditions of the test environment. Acceptance criteria remains same. Now, very important test which we all should be interested in is the fire resistance. The purpose of this test is to verify the resistance of the battery system against exposure to fire from outside of the vehicle. Example, a fuel spill from a vehicle. And in this test, the device under the test is subjected to direct and indirect exposure to a flame produced by combustion of a commercial fuel. Now, this test is a quite dangerous test. I have physically witnessed myself quite a number of times, and it is conducted in 4 phases. So this is the first method in which the fire test is conducted, which is a gasoline pool fire test. So the phase 1 begins with the preheating. So as you can see in the diagram, this is the tested device, means the battery system RESS, and a fixture. So there is a fuel in the pan, which is ignited at a distance of 3 meters from the tested device in the preheating phase. And it is carried out for about 60 seconds, just 3 meters away. This is phase A, which is the preheating phase. Then there is a phase B, which is the direct exposure to the flame. Here the battery system is exposed to the flame from freely burning fuel for 70 seconds. So this burning pan, this is shifted from this position, which was 3 meters away, to directly under the battery. And the test is carried out for 70 seconds. Phase C, in phase C, there is an indirect exposure to the flame. So after 70 seconds of phase B, there is a screen that is placed between the pan and the tested device, and the test is again run for 60 seconds. So if some manufacturer, they want to conduct a worst case criteria, they can run the phase B only for another 60 seconds. That will be a worst case for them. Phase D, which is the end of the test, the burning pan covered with the screen is moved back to the initial position. And after this phase, no extinguishing of the testing device shall be done. After removal of the test device, surface temperature to ambient temperature has been decreasing for a minimum of 3 hours. And the acceptance criteria for this entire test is that during the test, there shall be no evidence of the explosion in the battery system. Then another important test is the external short circuit protection. The purpose of this test is to verify the performance of the short circuit protection. In this, the device is intentionally short circuit by connecting the positive and negative terminal of the devices, and there is observation period for 1 hour, after which it is accepted. Then there is an overcharge protection, in which the device is deliberately overcharged to see the response of the device to the overcharging. Similar to overcharging, there is over discharge protection. Again, it is discharged to a level below. So in this, the acceptance criteria is that the device should inhibit the overcharge or over discharge, or else it is discharged to 25% of its nominal voltage. Then over temperature, in this, the device is repeatedly charged and discharged with the constant current, and then placed in a climatic chamber, wherein the temperature of the chamber over oven is gradually increased. So after all these tests, we can definitely say that yes, if proper testing as per standards are carried out, then definitely EVs are safe. Now, next thing is, how is type approval affected, particularly for EVs? So if we see, this is the entire list of tests that we conduct for a whole vehicle type approval for a normal vehicle. And there
I'm so sorry to interrupt, but you would have only 1 more minute to end this.
Okay. So there are no further changes, like only the type 1 test requirement, which are the mass emission requirements. They are no longer required. And this electrical safety test, which we have discussed in the previous slides, will be added to these tests. Quickly moving on to the European type approval. So this is the vehicle type approval, provides a mechanism for ensuring that vehicle meets relevant legislative environment and safety, and worst cases established using technical expertise. Regulatory mechanism of Europe, there are 2 regulatory mechanisms. One is the EU directives or the regulations, and the UN regulations. About VCA, VCA is an executive agency of the UK Department of Transport, which is a part of UK government, and it is the designated UK type approval authority and technical service for most new and on and off-road vehicles. And VCA is also the designated body for certification of packaging used in transportation of dangerous goods. VCA has also been appointed as a technical service to SNCH, so we can also provide E13, E5, and E4 certificates. Where VCA sits within the Department of Transport. So here you can see it's Department of Transport, Secretary of State. There is a parliamentary under Secretary of States, and here is VCA, DVCA, and DVLA, which are comprises different units of DOT. VCA has offices around the globe to meet global demands. In India, we have our offices in 3 major cities, 3 automotive hubs: Delhi, Pune, and Chennai. VCA India was launched in 2006, and engineering presence already established in 3 locations. There is a further plan of expansion in other cities. Aim is to enable automotive industry to compete on the world stage for road safety and environmental statistics.
Thank you, Mr. Bangia. That was a wonderful, wonderful session.
Thank you for your time.
Reached the end of the time. Now I would request Mr. Ankit Sharma, Business Development Manager, Automotive Technologies, to take the podium.
Hello. Good afternoon, everyone. And first of all, I would like to thank you, the team of Mobility Outlook, for organizing this event and giving me an opportunity to share my perspective on the future of two-wheeler powertrain. My name is Ankit Sharma. I am a business development manager and also leads the electrification topics for automotive division in Infineon India. Today, in next 20 minutes, I'll be taking you through a quick introduction about Infineon, evolution in the two-wheeler powertrain, two-wheeler powertrain components, which are the critical ones, and the differentiating technologies and quality, which Infineon offers to mitigate the challenges in these critical components. To start with, Infineon at a glance, on the left-hand side, if you see, decarbonization and digitalization are two key pillars for Infineon. And the entire company is aligned for innovation and addressing the challenges in these two megatrends. Decarbonization is mainly driven by CO2 savings, sustainability, and energy efficiency, whereas digitalization is mainly driven by productivity, comfort, and new use cases. If you look at the Infineon finances, Infineon is a 11 billion euro company as of last fiscal year, and we grew 30% YOY from FY20 and from 8.5 billion euros, and the main chunk of this revenue or the growth is coming from Cyprus acquisition. On the right hand side, if you look at the revenue by segment wise, Infineon is split into 4 different segments: automotive, industrial power control, product and sensor systems, connected secure systems. Automotive being the largest and contributing 44% of the overall Infineon revenue. The revenue by product category wise, if you see, the automotive has got very comprehensive portfolio, not just within Infineon, but even in the entire industry. We are the only company who has got a very comprehensive portfolio. We have the products from sensing to compute to actuation. From this graph, you can actually make out that 55% of our revenue is coming from power semiconductors, followed by 28% from microcontrollers, and then RF sensors and memory ICs, which are very important for storing some important data. Moving on to the next slide, which is again, as I mentioned, Infineon is #1 automotive semiconductor manufacturer, having a market share of 13.2%. Out of $35 billion, and we are growing YOY, and with the electrification and the new technologies coming in, this growth is expected to go much faster. In the interest of time, I'll quickly move over to the new style, next slide, or even the real topic of today, which is the evolution in powertrain. So two-wheeler is not new to India. Two-wheelers is there for a while, if not for a couple of years, even for a couple of decades. I would be talking about few technologies from the last couple of years. Even last couple of years, we saw that when the emission regulation BS4 was there, the motorcycles or the two-wheelers were driven with the technology CDI, capacitive discharge injection. Eventually, it got evolved to, after the implementation of BS6 with more stricter emission norms, it got evolved to electronic fuel injections or e-carburetor. And we also have a new BS6 OBD 2.2 around the corner. Now, government is planning to roll it out in April 2023. This would require a little more modification in the electronic fuel injection. Will need an additional auto sensor after the catalytic converter. For a better for a stricter with the strict emission norms, and basically the lower one, electrification. This is one of my favorite topic, mainly driven by FAME2 subsidy and also driven by rising fuel prices. Today I would be talking about the powertrain components, the critical powertrain components of electric vehicle. If you look at the block diagram on the right hand side, this is the block diagram of an electric vehicle, and the main powertrain components in this electric vehicle are basically PMSM motor, inverter, battery management system, and lithium-ion battery. Inverter is basically a motor controller, and as the name suggests, motor controller, it helps to spin the motor as well as control the motor. Battery management system manages the battery. It ensures the health of the battery, and it also keeps a track of state of charge, state of health, does the diagnostics, also does the communication with the entire vehicle, with the other components of the vehicle. In my coming slides, I would be deeping down. I would be deep diving into inverter as well as battery management system, which are most safety critical components. And so moving on to electric two-wheeler powertrain components. The first one is inverter. Inverter is also known as motor controller, as I mentioned. So on the inverter side, left hand side, it is basically the block schemes of the inverter, and right hand side, if you'll see, this is the system solution offered by Infineon of 5 kilowatt to 10 kilowatt. This is a reference design which helps enable our customer to take a big leap while doing the development for 5 or 10 kilowatt inverter. To start with, this inverter has got a dedicated MCU, which is basically which runs a FOC algorithm. FOC is a closed loop software, also known as field oriented control. It takes the inputs like current as well as rotor position and gives an optimum torque to the motor. And the next one is three-phase driver IC. Three-phase driver IC is basically a MOSFET driver. It takes the inputs, PWM input from the microcontroller, and switches the MOSFETs ultimately, and MOSFETs are further required to spin the motor. Those are on the actuation side. And the three-phase, in the typical scenario, this three-phase gate driver IC, in typical scenario, our OEMs that we have seen uses 3 discrete hub bridges. However, Infineon has got a solution which has got an integrated 3 hub bridges into one chip. The next one is the MOSFETs. These basically, there are 6 MOSFETs, 6 switches, I would say. 2 switches are required to spin, 2 switches are required for one phase. There are 3 phases of the motor, and hence these, even in some cases, we also need to parallel these MOSFETs to derive more current for the bigger motors, like for 5 kilowatt or 10 kilowatt motors. So these MOSFETs are on MOSFETs from Infineon are parallel friendly as well, and this is basically on the actuation side. Next one is about current sensors, very, very important component. In the inverter, current sensors are basically required to sense the current at each phase of the motor and provides the feedbacks to the microcontroller for FOC control. We got some modules ready along with our partner, and it's a plug and play. Our customers can easily use this to sense the current of each phase. Another one is rotor position sensor. This is again required to sense the angle of the motor and provides the feedback to the microcontroller for the FOC control. Last but not the least, the DC-DCs or safety power supply. Basically, this is the food for these devices are the food for all the power component, not just the power component, all the components, active semiconductor components in this block scheme, and they provide the appropriate voltage and current to keep them in healthy function. And also for an application like inverter, what we have seen is OEMs are preferring SLD compliant components. They want to have SLD certified products, and they're going for SLD certifications. However, there is no mandate, but since these are very safety critical applications, customers are looking for SLD components, and a microcontroller from Oryx or 3-phase gate driver or even the safety power supply, they all are SLD compliant. The microcontroller Oryx basically is the only SLD certified microcontroller in the automotive industry, and very, very powerful, and been acceptable and is acceptable by most of the customers, most of the OEMs across India as well as globe. Moving on to the next critical component, very, very critical component, battery management system. I would say most critical component of the electric vehicle. It also has got a dedicated microcontroller. If you see the block scheme on the left hand side, right hand side, we have got our own reference design with the BOM, with the bill of material, active bill of material from Infineon listed just below it. And it has got a dedicated microcontroller. This microcontroller helps to communicate with the entire vehicle. Also does state of health, state of charge, and all these are being managed by the microcontroller. The next important device, the cell balancing IC or the cell sensing IC mentioned in the block scheme, is basically this helps to sense the voltage across each cell also sense the voltage across each battery module, also helps to sense the current across each battery module with the help of this current sense, and also keeps an eye on the temperature of each cell. It also has got temperature sensor, also diagnostic. It has got 12-channel ADCs, which helps to sense all these parameters and provide that information to the microcontroller. Next one is basically battery disconnect switch. Battery disconnect switch, the function of battery disconnect switch is to disconnect the battery and the BMS from the entire vehicle. It is required at the time of charging or discharging. Also, in case of some hazardous event, in case microcontroller sense there is something wrong with the batteries or something wrong with the BMS, it immediately gives a signal to the gate driver that please ask Mosfets to cut off from the entire vehicle. Next one is pressure sensor, and pressure sensor is another, I would say it's good for sensor fusion. We already have a temperature sensor to sense the battery cells. However, what we have been advocating with the OEMs for last 2 years to incorporate pressure sensor inside the battery packs. So in case of any thermal runaway, pressure is the most sensitive parameter which can be sensed quickly, and it can give an early indication as early as 5 minutes before to the rider that there is something wrong with the battery, there is some leakage in the battery, and rider can go find a safe place for himself. Of course, it doesn't guarantee any it doesn't guarantee anything, guarantee any safety. However, it's good to have this more sensors to have more data and keep BMS to have more safety and to add more safety to the BMS. Next one, differentiating technologies and quality from the Infineon. Since I discussed about inverter as well as battery management system, the critical components of the electric vehicle. So I also would like to take you through the challenges that we are addressing in these areas. And I would also like you to give some overview about the technologies that we have to address, which are addressing many challenges in these areas. Yes. So first thing first, automotive quality is the need of automotive OEMs for critical applications like inverter and PMS. Infineon has got a zero defect policy. That means to achieve a zero defect policy, zero defect over 15 plus years of product lifetime, we have to go beyond AEC-Q standards. So if you look at this bathtub curve, right, it shows the failure rate over time on the left hand side and on the y-axis, and on x-axis it shows the lifetime. That is, we stress our devices, we test our devices up to this. As per AEC-Q standard, it is 1000 hours, and as per Infineon standard, we test them to 3000 hours. There is a reason behind it. So if we try to use any consumer product, it would be very, very risky to use in this safety critical applications. Even if we talk about the AEC-Q standards, these standards are basically tailored for well-known applications, and it may fail to cover newer applications or emerging applications which has more stringent mission profile, applications like electric vehicle or ADAS. And also this AEC-Q standard does not basically just provide this AEC-Q standard only. For example, if you get this AEC-Q standard, if your product get your product AEC-Q qualified for one time, it is qualified for the life, which does not talk about any stability of the manufacturing process over the lifetime. Hence, it is necessary but not sufficient for emerging applications or critical applications with high number of electronics to have this AEC-Q, to qualify AEC-Q. So I'll just quote a very simple example to you. For example, if you talk about a classic engine or a classic bike, the average number of use of Mosfets is hardly 6 to 8 numbers. However, on an average, in an electric two-wheeler rated of 5 kilowatt hour equivalent to 100 cc of engine, 100 cc of performance, those MOSFETs count is increased to 50 units per bike. That means ACQ standard, basically the failure rate of ACQ standards is in 1 defect per million. That means if we reverse calculate, that means every 20,000 first vehicle will have a failure. Can OEMs afford to have that kind of failures? The answer is no. Hence, Infineon has got some application know-how, has some process control, has some system know-how, and we also have some design goals. With that, we are able to manage this failure rate and reduce it to 50 defects per billion. We are no more talking about defects per million, which is as per ACQ standard. Hence, with the newer emerging applications like electric vehicle, ACQ standard is not sufficient. Hence, we have to go beyond these standards, and with the experience which Infineon has in automotive for last 40 years, we understand these application or requirements very well, and we came up with the 50 defect per billion kind of defect rate. And we with the stringent mission profile, because inverter is a very high switching application, a lot of thermal cycling happens in that. So we test our devices for a longer duration of 3000 hours, so that there should not be so that we should be able to offer a very robust and reliable product to our customers. Moving on to the next one, silicon carbide is in the talks for a while now, and silicon carbide is a wide bandgap technology with advantages like very high thermal performance, ultra low losses, and high voltage capabilities for the same size as silicon. Compared to silicon carbide is faster, smaller, and more efficient, which actually leads to higher switching frequency, higher power density, and lower losses, resulting in high voltage battery saving. If you look at basically this silicon carbide in two-wheeler, it only makes sense for very high performance bikes. And if you see, it only makes sense if you have a battery capacity of more than 50 kilowatt hour. So that means that is a very heavy battery, and it's currently being only used in very high performance bike, and doesn't make sense for a regular 100 cc or equivalent or 150 cc equivalent bikes. Moving on to the next technology, a topside cooling technology. This is one step up technology for the automotive MOSFETs. It has got 20% better thermal resistance. With this solution, basically this kind of solution is very good when you scale up the power level of a motor controller or inverter. If you see if this MOSFET, the drain is on the top of the MOSFET. And here you see this MOSFET is sandwiched between heatsink and PCB. That means the heat is directly extracted from the top of the MOSFET, and the PCB will have a very lesser impact, and there would be much better thermal performance of the MOSFET for very high switching applications like inverter. Moving on to the last slide, basically chip embedded technology. Again, most innovative concept in the automotive market. This concept is somewhere in between the bare dies and packaged chips, resulting in the lowest RDS(on), and Infineon has already proven this concept, and we are working on the cost optimization. So this basically, in this case, we embed the chip inside the PCB, and the heat is spread across the PCB. We have a partner in Europe with whom we have worked on this concept. And moving on to the last slide. So basically, just to summarize, Infineon is a key enabler for the sustainability and decarbonization, and we are ready today with our technologies for revolutionizing the future of electric vehicle with all the technologies which I mentioned about, for example, silicon carbide or the topside cooling MOSFETs, or even the chip embedded technology and the Infineon quality, also the Infineon automotive quality. So we are ready to take on the electrification of tomorrow. So with the automotive, it's not just the products, but with also the automotive know-how, which Infineon has, also the automotive quality, and also we have system expertise. Also, we have two-wheeler center of competence, With all this put together, these are the key differentiators for our customers who work with us in this electrification journey. With this, I would like to thank all of you, and a special thanks to the audience who listened to me patiently. And if there are any questions, I would like to take them. Thank you.